Thank you. Cool. Thank you all for coming. I hope you enjoyed this talk as much as I enjoyed it putting together, and you also learn as well. So the talk is about embeddings. It's about Yu-Gi-Oh cards. You don't need to know Yu-Gi-Oh cards, but just a quick show of hands. Who has played Yu-Gi-Oh cards before? Great. Amazing. Yeah, I mean, I was aiming for that audience, for them to come here. So who still plays Yu-Gi-Oh today? Okay. Yeah, okay, that's great. That's great because I mean, I've lost track of the game. So please don't, nobody will criticize me about my takes on Yu-Gi-Oh, current Yu-Gi-Oh. Cool. So that's me. As they mentioned, I'm a senior MLOps engineer at Simply Business. However, this talk has nothing to do with my company in terms of like, I'm not doing this for a job, for a living, right? This is just, again, as I said, that's a silly little project. I'm a Python enthusiast. You can find me on Twitter or Threads. I'm trying to tweet more in English. Most of the time, tweet in Spanish because that's my native language. And I also make YouTube videos. So again, just in Spanish. Before we get on, some of you have already a card that looks like this. If you haven't got one, at the end of the talk, I had to print like hundreds of them so that they were cheap. So if you want to grab one of them, they're at the chair at the front. You can get there the code, the slides, and a link to the demo that hopefully we'll get to see at the end of the talk. So I'm going to give you just a brief introduction to Yu-Gi-Oh! And what we are trying to solve. I'm going to talk to you about what are embeddings and what can we use them for. And I'm going to show you how to create embeddings using a co-occurrence matrix. And at the end of the day, at the end of the talk, hopefully there will be some time for a demo. Otherwise, you can just view it on your own in the link that I've provided. Cool. So Yu-Gi-Oh 101. Yu-Gi-Oh is a trading card game where you can collect cards, but most of the time people use them to play against one another. People draw cards from a deck, and they take turns to play them onto the field. These cards are monsters, spells, or traps, and all of them interact with each other. And the aim of the game is to reduce the life points of your opponent to 0. So this is how a card looks like in Yu-Gi-Oh! This is my favorite card as a kid, still as an adult, or an overgrown kid, as someone might say. These cards have different attributes. So they have I'm being redundant. They have an attribute called attribute. They have a card name. They have a level. They have certain artwork. Some of them have an attack points, defense points, effects, and so on. So this is how another card looks like in Yu-Gi-Oh! So this is a spell card. We're not allowed to call them magic cards because there is a game called Magic, and they have like a lawsuit and so on. So this is a spell card. Like this, there are many types of cards. There are different types of monsters. And yeah, as I mentioned, the Yu-Gi-Oh! Back in the day is not the same as Yu-Gi-Oh! Nowadays. There are many different kinds of monsters. But the point that I'm trying to convey here is that these cards have different attributes, each one of them, and they interact with each other. Now, I mentioned decks because players assemble these cards into decks to play. So they spend a lot of time crafting the perfect deck so that the cards that they put in it interact very well with each other, because like remember, the aim is to play a game and reduce the life points of your opponent to 0. So now, let's think about, let's say I want to recommend new cards to players, or I want to recommend cards to players. So how do we go about this? Just imagine, look at these cards. You might start to notice certain similarities between them, right? So some of them have like similar art, some of them have similar names, similar effects, similar types. But how can we tell they are related? For some of you, the ones that you didn't raise your hand, it might be hard to tell like how these cards similar, right? Even for a new player, let's say some players just focus on a specific type of game or a specific strategy. So if they see a new card, it might be hard for them to like understand or find related cards. Okay, let's pause that for a bit. Let's stop talking about Yu-Gi-Oh! I'm going to talk to you about embeddings now. So embeddings are a way of transforming unstructured or high-dimensional data into something that is more compact, that is more meaningful, into something that we would call a meaningful representation. The idea of embeddings is so that we end up with a bunch of numbers that represent the content content of an object into something that we also could call a vector. A vector is just a bunch of numbers. So in this case, imagine we could turn that card into certain values, into certain numbers. This also has the benefit that a computer now can process a card, because if we show a card to a computer, it won't understand like what the hell is going on. It might see an image, it might be able to recognize some text, and so on, but it doesn't recognize the card as an entity. Another advantage of having embeddings is that we can now store cards or any other entity that we have embedded. We can store it, we can query it, we can compare against each other. This facilitates the analysis of complex information. And yeah, as I mentioned, the embeddings capture semantic information into what we could call a compact way. But of course, embeddings are not without a fault. So when we try to compress complex information into something that is compact, we lose fidelity. So in certain cases, or in most of the cases, I would argue, you need to verify that the embeddings you're creating are actually capturing the entity that you are compressing, that you're embedding. And something else that gets people confused is that, yes, we can create an embedding for a certain card, but we cannot recreate the card from the embedding. So for example, in my case, imagine we have this card that has attack points that has a certain level. We cannot say, okay, so this number in the vector represents this level. Or we cannot say, okay, this card has like 0.8 in this entry, in the vector entry. This represents 2,500 points of attack. So yes, remember, you can go from card to embedding, but you cannot go from embedding to card. And the same goes for anything else you embed. The cool thing is that we can create embeddings for cards, we can create embeddings for images, we can create embeddings for text documents. That's actually very relevant. In this conference, I've seen like 1,000 talks about graph. Most of them rely on embeddings to work. Surprisingly, you can also create embeddings for food recipes. So if you have seen these companies like HelloFresh or Blue Apron and so on, most likely they're working with the recipe embeddings to give you recommendations on what to eat next. And yeah, if we have time, I can show you how to create embeddings for recipes if you want. So there are many ways we can create embeddings. Some of them are prediction-based. These are very well-known algorithms in the, I think by this point everywhere, but in the academic circles. One of them is called continuous bag of words. The other one is called skipgram. And more recently, we can create embeddings using LLMs. There are also what we know as frequency-based embeddings. So some of you have performed already like data analysis, creating like count vectors or TF-IDF. Those are embeddings. And there is also the one where I'm going to focus on this talk, the concurrence matrices. We can also have ad hoc embeddings where you get like a bunch of experts to give you like certain values for attributes, let's say in the cards or in your recipes and so on. But these ones are very tricky to create, and obviously they're very expensive to create. Cool, so yeah, on to the focus of this talk. And we go back to Yu-Gi-Oh! So again, I'm asking, how can you tell that these cards are related? Again, they have like similar artwork and so on. But how about we just gather a bunch of experts of Yu-Gi-Oh! And then we trap them, we keep them in hold forever, until they can come up with some way of transforming these cards into these magic numbers that I've been talking to you about. Obviously, we give like cards away or something like that, they might be happy to cooperate with us, but it's not a feasible solution. So how about we look at the players, but we don't trap them, we don't force them to do anything, and we just have a look at what they already do. So we can have a look at their decks. We can have a look at the cards they put into these, as I mentioned, they spend hours, and there are like in online forums and tournaments where they literally just go there and discuss about the strategies and which cards go well with one another. So yeah, because they want to increase the chances of winning. So yeah, the question is, can we exploit this information? And yeah, the answer, as you might imagine, is yes, we can exploit this information. And again, we don't have to do anything. We just have to look at what they already do. So for this talk, I visited this website, which is an amazing community of Yu-Gi-Oh! Players and enthusiasts like me. I mean, again, I look at the game nowadays and I just don't understand what's going on. But this is a nice resource if you want to get back into the game. Yeah, the community is called Yu-Gi-Oh! Or Yu-Gi-Oh! Pro Deck. And they have forums, they have card lists and decks and so on. The cool thing is that they offer something that is more friendly for us programmers. So they have this cards API where you can just literally go to the URL and they're going to give you the list of all the cards. There are around 13,000 cards nowadays, and you can just get them with a simple API request. But yeah, a very important part of this talk and what we are going to do is the decks. Sadly, they do not offer a decks API, but the solution is just right there. They have a web page, and this web page is very, very easily web scraped. So that's what I did. At the end of the day, I ended up with 13,000 cards and more than 100,000 decks. This data set is available in Kaggle, so if you just want to go and have a look at the data set. By the way, if you want to support Yu-Gi-Oh! Pro Deck, you can get a premium subscription. Otherwise, you can just use their API or web scrape their data. So not a big issue. Just a parenthesis, the data set, as I said, the data set is available in Kaggle. I have many other data sets. I'm going for my Grandmaster in Kaggle. So if you can have a look at the data sets I already have of both them, that would be great. But yeah, enough about me and promoting myself. So on to the data processing. And yeah, just remember, if you want, you can take pictures of the slides. Just make sure I'm in the picture. Otherwise, just have a look at that link. If you take anything from this talk, just let it be that link. You'll be able to find again the slides, the code. You'll be able to reproduce this whole thing at home, basically. So the first thing you have to do is to build a map. Remember, I told you that the cards have a passcode, and we have to turn this passcode into a continuously increasing number, just so that we can use these cards now as indexes, or indices, I don't know how to say it in English. And we're going to process each deck one by one. The point of processing each deck one by one is because we want to fill a concurrence matrix. So after we calculated the indexes for our cards, remember that's just basically giving 0, 1, 2, 3, 4, and so on to each one of these cards. We're going to create a matrix that is going to be of size n by n, where n is the number of cards. In this case, remember, it's close to 13,000. So we're going to end up with a matrix that is 13,000 by 13,000. And then we're going to add a 1 where each card occurs with one another. So each card is going to be once represented in the columns and also represented in the rows. So at the end of the day, we're going to end up with something that looks like this. In this case, I just processed just a few cards, but the goal is to end up with a matrix that looks like this. Yes, like a black square. The problem with this is that we're going to end up with a matrix, since we had, remember, 13,000 cards. We're going to end up with a matrix that is 172,554,496 entries, where only 5% of them has a value different from 0. So we got ourselves an almost empty matrix. By the way, this is already an embedding, because we could take each one of these rows, and remember, each row represents a card. That's already an embedding, because it's a numerical way of representing a value. But again, remember, this is mostly filled with zeros, because that's what happens, right? Not all cards not all cards are represented in the decks. Not all cards happen along with each other in the same deck. So that's what we got. So remember, we have only close to 10 million non-zero entries in this matrix. And here's where the next step comes in. So we're going to go from having this matrix, which is like a black square in there because it's full of zeros, to have dense vectors. How do we do that? So we can decompose this matrix. And there are two main ways of decomposing a matrix. In this case, I went for something known as singular value decomposition, or SVD. And singular value decomposition looks like this. So we have a matrix. In this case, you can think of this matrix M as being our 13,000 by 13,000 matrix. and it's going to be decomposed into 3 matrices. So one of the matrices is called U matrix, or the left singular vectors. That is going to be of size n by m. Just keep an eye on the dimensions, by the way. In our case, since we have like a square matrix that is 13,000 by 13,000, these sizes are going to be the same. But in some other cases where you don't have exactly like a co-occurrence matrix like I have, you're going to have like these different sizes of matrices. So just going back to like the example in specific. So we're going to end up with 3 matrices. One of them is called the left singular vectors. One of them is the singular values. And the other is going to be the right singular vectors. You don't have to focus too much on this. The point that the point of doing this decomposition is that at the end of the day, we're going to have these 3 matrices that when we multiply them together, we're going to get back our original matrix. Remember that is basically filled with zeros. A cool trick that we can perform using this, doing this singular value decomposition, is that we can just take some values out of it. And that's going to be your embedding size, the size of the vector that you want to get out of this transformation. So in this case, let's say we want to truncate, or to get like an embedding of size 50. We just have to truncate these matrices by just get, let's say, the first 50 entries of each one of them. And surprisingly, we're not going to get back, if we ever try to multiply these matrices after truncating them, we're not going to get back the original matrix. We're going to get an approximation of it. And this works because, I mean, mathematics, thankfully, and some linear algebra going on in there. So let's say in my case, I kept 50, only the 50 most important vectors, because that's what SVD does for you. If you truncate it to 50, if you truncate to some other value, you're going to get the top most important values anyways. So now this is how these matrices look like for us. So we're going to end up, we went from having a 13,000 by 13,000 matrix to having a 13,000 by 50 matrix that we can then use. So that's what we're going to use. Usually, if you want to get the embeddings for the rows of your matrix, you have to use the left singular vectors. If you want to use get the embeddings for the columns of your original matrix, you have to use the other matrix, the left singular values. In our case, remember, our matrix is basically a concurrence matrix, so we have the same values for the rows and the columns, so it doesn't really matter which one we use. In my case, for the purpose of the code that I'm about to show you, we're going to use the U one, or the right singular values. If this was too much because honestly, I don't understand this singular value decomposition that much. It was easier for me to see it in code. So that's how the code looks like in Python. I'm going to explain you line by line. So we use this method from this function from SciPy that is called SVDS. We're using this SVDS, even though there are like truncated SVD, and there is a method in NumPy called SVD, because SVDS has this nice trick where you can just calculate a partial matrix decomposition, which is what we want. Remember, we want to get only a partiality of it. We don't want all the values. Otherwise, singular value decomposition takes some time, and if we just want some of the values, then there is no point of calculating the whole decomposition, right? We just want a few. We just want some vectors out of it. So that's why we're using SVDS. SVDS takes our matrix, our original mostly zero field matrix, and it takes a value called k. And in this case, I'm setting it to embedding size. I know that embedding size is not declared in there, but embedding size is just an integer. In my case, I set it to 50. Then remember, SVDS returns 3 matrices, U, sigma, and V transpose. As I mentioned, we only care about U. S is for some other purpose you'll see in the code, but we don't care about the other one, V. So we're just basically discarding it. The next step is multiplying U by the square root of the singular values. This is not a strictly necessary step. This is just scaling those vectors. Usually, when you want to use, when you're going to deal with machine learning downstream tasks, you usually want to scale your values back, so they don't end up exploding your parameters in your neural network and so on. So this is a recommended step. You could also play with this. Think about it as another hyperparameter to your embedding. The same goes for this for the transformation, where we just are standardizing the values, just like centering around the mean and dividing by the standard deviation. And at the end, we're going to have in embeddings, in the variable embeddings, our embeddings, what we're after. So effectively, we went from having a matrix that is 13,000 by 13,000 to have a matrix that is 13,000 by 50, which, again, just to give you a brief comparison, we had a matrix. Obviously, these are not a scale or anything. But what I'm trying to show you here is that now we have more like a live matrix that is full of values, that has full of numbers, because all the information is compacted into this dense matrix. Now this is how a card looks like. It doesn't look like a bunch of stars, doesn't look like an artwork or anything. It just looks like numbers. So now we can do cool things like running queries on our cards. So yeah, we have vectors. Now what? So now for this part of the talk, we have to make a few assumptions. So we have to make the assumptions that the previous calculations, all these singular value decomposition and so on that we did, created vectors that actually represent our cards. We have to assume that similar cards are close to one another in this vector space. And then we have to assume that given we have a vector, we can find vectors that are close to each other, and those entities are going to be similar or close to each other in real life. So for example, we get an embedding for a card, and we can find those that are near that vector and find similar cards. For this demo, and I also recommend you have a look at this library. It's called Annoy. It's a library from Spotify. It's actually a C++ library that has just Python bindings around it. It's useful to store vectors and to query them. I really like using this to create like proofs of concept, because it's just a single index. It just creates a file, and basically that's your vector database. As far as I know, Spotify still uses it for some production use cases. But again, I use it mostly for demos. And then if it proves the demo has a value, then we go on and scale to something else. Cool. So now on to the demo. And this is where, if you already know Yu-Gi-Oh, then forgive me if these recommendations are not that great. But yeah, now we can go ahead. Oh, sure, perfect. I wasn't showing anything. If we go ahead, we can just select a card, and we'll find similar ones. So Annoy gives us something called the distance, and obviously closest is better. So let me try with my childhood, my favorite card. So yeah, so for example, the Dark Magician, those are the suggestions we get. Does anyone have any card that would like me to try? John? Okay. Yeah, perfect. Yeah. For those that you know, Pot of Greed is like called like a staple card, because all the people have that in their decks. So that's actually a really good point, because in those cases, like embeddings do like funky things, because that card is in a bunch of decks. So that embedding might not be as representative of that single card, right? So let's just try Pot of Greed. Cool. So you get, basically, for those that know, a bunch of these cards are basically banned from the game, because they're like super powerful. So therefore, they're bound to end up together, right? Any other suggestion?
One of the god cards, but I don't remember the name.
Oh yeah, I remember those names.
Oh, Exodia.
Yeah, I'll do Exodia, and then I'll do. Yeah, so I mean, we got some god cards as well, and yeah, it's a funny story. So I started doing this project during lockdown. Everyone went crazy with things, right? And I was like, okay, I have extra money because I'm not going to the office. I'm gonna start buying Yu-Gi-Oh cards again. Then I realized that it's a very expensive hobby, so I might as well just collect the cards digitally. So yeah, there you go. That's my collection. Yeah, let's just try. So Exodia is a monster that has, it's a monster that is divided in parts. So we will assume that if we get a part, if we want to get recommendation for a specific part of that monster, we're gonna get recommended the other parts. So let's just try that. Exodia. Cool, yeah. I mean, that went really, really wrong. So yeah, you can see there is a head in there. We're supposed to get the arms and the legs. So let me just try with the, do you remember how the name of the specific part is? Left. Oh, it was. Okay, let's just do left arm. Okay, so yeah, that we were, given the head, we were supposed to get that. Yeah? Okay. Okay, so if I can take anything from, like, let's say if I search for the head of the monster, that makes me think that the head is being played along with other cards, not necessarily with the rest of the body of this monster. Cool. So yeah, again, just this demo is live. You can just go and have a look at it. If it breaks in some spectacular way, like you can come back and tell me, you know what, this recommendation makes no sense. I'll be more than happy to keep working on this. Okay, so conclusions. Are these embeddings perfect? No, not by any means. We have to evaluate them, and the same you have to do the same. You end up creating embeddings. So there are these two methods of evaluating embeddings. One of them is intrinsics, where you have just a look at the embeddings themselves. So for example, you can ask questions like, do similar cards end up together in the vector space? Or are we generating meaningful clusters? So what you can do with your embeddings is to clusterize them using k-means or something like that, and have a look at the clusters. If they make sense to you as a subject matter expert, or if you're not an expert in Yu-Gi-Oh, just get someone to check your vectors. That's a good measure. Or there is this other way where you can measure the quality of the embeddings extrinsically. So for example, if we end up using these embeddings for a machine learning task, if that machine learning task ends up being successful, accurate, or has high recall, or whatever metric you have, if that ends up being good, that means the embeddings are good as well. So remember, intrinsically, just have a look at the vectors themselves, or extrinsically, use them for a downstream task. Again, this data set, the data set I use is heavily biased because some cards are not well represented. Some cards are literally trash. Like I tried to sell some of the cards that I have. The person told me, you have to pay me to take these cards because these cards are useless. Nobody plays them anymore. And yeah, this data set is heavily biased towards competitive play. So I just want to show you how a modern deck looks like now. Yes, you can see that there is not a wide variety of competitive cards. So a lot of people just play like 3 of the same card over and over again. So this data set, it looks like that. So yeah, just have a look at the data set you're using to create your embeddings. Okay, so what's next? For example, with this data set, we can obviously improve the embedding quality. We can ask proper subject matter expert how do these embeddings look like with a tool like the ones I showed you, just like search for similarities. Or you can use them, maybe you can try to predict the outcome of a Yu-Gi-Oh match, or we can use this to recommend negative cards. So for example, I showed this thing a card, and I want this an algorithm to tell me, okay, so which card do you recommend me that counteracts this other one? So that's something that we could do with embeddings, specifically the Yu-Gi-Oh card embeddings. Obviously, if you have another use case for embeddings, you'll have to come up with your own tasks. So what I hope you take away from these talks. Embeddings are a numerical way of representing complex data. In this case, my complex data was a Yu-Gi-Oh card. You can use it for your own data sets. Embeddings are numerical representations. These are dense numerical representations where you have a bunch of values compressed together, unlike a dense matrix like the one I show you. And there are several ways, mainly using neural networks and concurrence matrix. And we can exploit already existing data. Like in my case, it was players building decks. And we didn't have to go and ask them, can you do this for us? They already do it for free. Okay, so cool. Thank you very much. You can find me in there. Remember, everything that you saw today is in the link. Yeah, I think now there is some time for questions. Thank you.